A system takes one or more input signals, processes them, and produces one or more output signals. For continuous time systems, we write x of t as the input and y of t as the output, connected by the operator h. The notation y of t equals h applied to x of t means the system transforms the entire input signal into the output. For discrete time systems, the same idea holds. X of n maps to y of n through the operator s. Systems can be as simple as a multiplier or as complex as an audio equalizer. What matters is that we can fully characterize their behavior through these 6 properties. A system is memoryless if the output at any time depends only on the input at that same time. For example, y of t equals 2x of t is memoryless. To compute the output now, we only need the input now. In contrast, y of n equals x of n minus 1 has memory because the output depends on a past input sample. Accumulators and integrators always have memory. Causality is related. A causal system's output depends only on present and past inputs, never future ones. Every memoryless system is automatically causal. A non-causal system, like y of t equals x of t plus 1, would need to know future inputs. This is impossible to implement in real time. All real-time physical systems are causal. Linearity is perhaps the most powerful system property. A system H is linear if it satisfies 2 conditions, homogeneity and additivity, together called superposition. Homogeneity means scaling the input scales the output by the same factor. H applied to a times x of t equals a times h applied to x of t. Additivity means the response to a sum of inputs equals the sum of the individual responses. H applied to x1 plus x2 equals h of x1 plus h of x2. Combined, superposition states h applied to ax1 plus bx2 equals ah of x1 plus bh of x2. A nonlinear example, y of t equals x squared of t. Check. H of ax equals a squared x squared, but a times h of x equals a times x squared. These are not equal, so the system is nonlinear. A system is time invariant if shifting the input in time produces the same shift in the output. Formally, if y of t is the response to x of t, then the response to x of t minus t0 must be y of t minus t0. We use a 2-path test to verify this. Path 1. Shift the input first, then apply the system. Path 2. Apply the system first, then shift the output. If both paths give the same result for every shift t0, the system is time invariant. Example. Y of n equals n times x of n is time varying, because the coefficient n changes with time. Shifting the input gives n times x of n minus n0, but shifting the output gives n minus n0 times x of n minus n0. These are different. A system is BIBO stable. Bounded input, bounded output stable. If every bounded input produces a bounded output. If the input satisfies the absolute value of x of t less than or equal to mx for all t, then the output must satisfy the absolute value of y of t less than or equal to my for some finite my. For example, y of t equals e to the t times x of t is unstable. Even a bounded input like x of t equals 1 produces an output that grows without bound. Invertibility means a system has a unique inverse. Different inputs always produce different outputs. An invertible system is one-to-one. Example, y of t equals 2x of t is invertible, with inverse system x of t equals 1/2 y of t. Non-invertible example, y of t equals x squared of t. Both x of t and negative x of t produce the same output, so we cannot recover the input. Let's test all 6 properties on the discrete time system y of n equals x of n plus x of n minus 1. This is a 2-sample averager that adds the current input to the previous one. Memory? Yes, the output depends on x of n minus 1, a past sample. Causality? Yes, it uses only the present and one past sample, no future inputs. Linearity? Yes, h of ax₁ plus bx₂ equals ax1 of n plus ax1 of n minus 1 plus bx2 of n plus bx2 of n minus 1, which equals ah of x1 plus bh of x2. Time invariance. Yes, shifting x gives x of n minus n0 plus x of n minus 1 minus n0, which is exactly y of n minus n0. Stability? Yes. If the absolute value of x of n is bounded by m, then the absolute value of y of n is at most 2m, which is finite. Invertibility? Yes. Given y of n and y of n minus 1, we can recover x of n recursively. This system is linear and time invariant, so it is an LTI system. Today we covered the 6 fundamental properties of systems. Memory. Does the output depend on past or future inputs? Causality. Does the output depend only on past and present inputs, never future? Linearity. Does the system satisfy superposition, homogeneity, and additivity? Time invariance. Does a time shift in the input produce the same shift in the output? Stability. Does every bounded input produce a bounded output? Invertibility. Can we uniquely recover the input from the output? A system that is both linear and time invariant is called an LTI system. LTI systems are central to signals and systems because they can be fully characterized by their impulse response, a topic we'll explore in the next lessons.